Welcome back, calculus friends. We just wrapped up our unit on limits review and featuring L'Hopital's rule for evaluating limits. This is intro to a new topic, and heads up, this is not on the AP test. This is the special 2020 special case do it at home test. However, this is good stuff, and I wanted to make sure that you were ready to go for next year. We're doing this more than just preparing for a one-day test, in this case a 45-minute test. We're getting ready for learning. So I do appreciate everybody hanging in there. Those folks that are still working on learning, that's who I'm working for too. The folks that are going to just kind of pack it in and say, yeah, YOLO, whatever. You know what my response to that would be. I would use every opportunity to learn and better myself is always my motto, and that's what I'm going to keep working on. I've got this worksheet posted. It says worksheet area between curves. That's what we're talking about today. Just wanted to highlight a couple things. The problems don't start until number 7. This is should be old review here, right? Take the derivative, no calculator. So you've got a product rule. Oh, we've got a quotient rule. Oh, we've got implicit differentiation. So this is a good review. So even though problems 1 through 3 are good review on derivatives, oh yeah, problems 4, 5, 6 are good problems for antiderivatives. So no calculator, because this is something you should be able to do. I posted the answer key. You've already got that available to you as well. But I wanted to give more feedback. What we're doing is going to be working on problems like this. Find the area bounded by the given curves. So the area between two curves, the area of a region. Drawing a graph, and in years past people tend to skip this step. I'm not sure how you can visualize what the problem is asking you if you don't draw those two. And as far as the word on no calculator, this unit, if this were a normal school year, I actually would let you probably use the calculators, because the setting up, clearly we're finding the area under the curve, so that should remind us of the integral. Setting up the problem a lot of times is the challenge. And sometimes the integrals are just so, I'm going to say interesting, you want me to say difficult, that you would need technology to finish the problem. So keep that in mind. I know my math lab problems usually expect you to be able to get exact answers. I'm not sure how I'll evaluate that when we get to quizzes and tests, but assuming we'll put the quizzes and tests into Canvas, remember you can always use your calculator if it's an exact answer that the answer is looking for. You can use your calculator to convert those exact answers as an answer choice into what your response might be. So I'm going to do the first few examples here by hand, but really we're going to start and review the opportunity to use our calculators as technology. So I've got my calculator handy, ready to go. All right, so again, review derivatives, review integrals. Today's lesson really starts with these problems, and the answer key is posted. So let's get started. In general, if we understand what we're doing, we're finding the area of a region between two curves, or the area, if we were just shorting it out, area between two curves, right? Well, the area under the curve, under the curve down to the x-axis, would be the integral from a to b. Okay, so we're going to draw a figure here, and I've got some function f. Okay, that's our f function here. And if I were to find the area, let's say from 0 or a to b or wherever, right, that area would be the area under the curve from a to b of f of x. Okay, I'm going to not put the dx in here for just a second. You'll see why in just a second. Okay, so that's going to find the area under the curve from here to here. So if we shaded this in, it'd be the whole thing. So I'll do a real quick shade. Okay, that would be the area under the curve from a to b. Okay, however, I might have another function here. This is our f function. This might be our g function right here. I'm hoping you can see the color difference. I can see it as I'm looking at what is on the screen here. So I'm hoping you can see that. But if I just did the area under the curve, wouldn't that give us this? The area under the curve from, let's say, A to B, right? That's not what I want. But if I were to subtract out minus g of x, now you can see I'm going to put in my dx there. I've got the area between those curves because the top minus the bottom, and I'll do it in squiggle hash or something like that here so you can see. This is the area between those two curves. If I've got the big area minus this area below the red curve, that should be able to give me that area between the curves. Okay? Keyword here that I want you to think about is top minus the bottom. Remember, this integral means accumulate. I'm accumulating a bunch of areas of rectangles. So I'm going to use this rectangle right here as an example. The width of this rectangle is dx. The height of that rectangle is this top value here minus this lower value here. So the height of all those times the width plus the height times the width plus the height times the width, accumulating all of that from A to B, is this area right here. Okay, so the area of a region between two curves. All right, this should not be a difficult thing, and this is not a challenging topic. If you were on the conference call this morning for AB, I actually used the word interesting. I might have even slipped in the word challenging or hard. Maybe it's a little challenging. This topic is a challenging topic. This one is the intro into what is challenging. So don't think, oh, I can't do it today. Yes, you can. Okay, so let's do an example or two, and we'll see how we're doing. An example. Find the area bounded by, and again, understanding what all those words are, read the question, okay? Because we're going to find volumes the next time we do some practice, and that will be something different. So bounded by this. Y, or we'll make a f of x, equals 2 minus x squared, and g of x equals x. So I'm going to quickly sketch a graph. 2 minus x squared is a parabola that's shifted up, that faces down. And the line g of x equals x, well, that's just going to be up 1 over 1, up 1 over 1, up 1 over 1. I would hope, and I'll put them in red dots here so we can see this, that this is the region here that we're trying to find. I hope we could see that that's the area bounded by that. On the one end, you've got this line here, and on the curved part, you've got the curve, okay, as the top boundary. Well, top minus bottom, or if I draw in my representative rectangle, it doesn't really matter where I draw it in as long as that rectangle works for the whole problem. Would you agree that from here all the way to here, the height of those rectangles is going to be the curve minus where the line is? The curve minus the line. And oh yeah, this is negative over here, but isn't this still going to give, let's say this value is 1 and this is negative 1. 1 minus negative 1, isn't that still a height of 2? I'm just making up numbers. It's not those numbers, okay? Or this is 0 minus 0.3. I mean, again, I'm making up numbers. We don't know what the height is. But it's negative, so 0 minus negative 0.3 would be a positive number. That height should be a positive number. The area here should be found as a positive value, okay? Even though this is below the x-axis, we're finding the area of this region. So that should give us a value that's positive. Okay, so there's no context where a negative area would make sense. One of the things that I need to figure out is this point and this point. Okay, now some of you are just going to use your calculator, and maybe on the next example we'll do that. We will. This one I want to know how to do that algebraically. So I'm going to solve 2 minus x squared and set that equal to x. My curve is 2 minus x squared. My line is x. I'm going to remember that I can, oh wait, I've got a parabola here, so an x squared term, I probably should make a 0 and make that a positive x squared. Move it to the other side, minus 2. Teach me how to factor, teach me how to factor. I hope you all remember how to factor. The only way to make an x squared is an x and an x. The only way to make a 2 is a 2 and a 1. We just need to figure out what our SIGN sign should be. X plus 2, x minus 1, to give us a positive 1x there. And if you do a quick FOIL, you could double check that. That means x equals 1 is this point right here, and x equals negative 2. Okay? So I'm going to find my area by finding an integral from negative 2 to 1 of what? Well, again, if you remember this and you remember this, you'll be good to go. The height of each of those representative rectangles and drawing the picture and drawing in the rectangle is the way to go, okay, is my curve. Okay, this is a dx because I'm adding up an incrementally small width of dx terms, but I'm accumulating them from negative 2 to 1. So my width of my rectangle is dx. My height is just going to be top minus bottom. Well, what's your top part? Isn't that 2 minus x squared? What's your bottom? So minus x. And then I'm going to say the width of those is dx. If you want to get that in standard form or in order that is better, we could do that, but it doesn't need to be. Negative 2 to 1. Oops, this is positive 1, sorry. Negative x squared minus x plus 2 dx. We'll do this one by hand. It's not a bad way to review. That's negative 1/3 x to the third, right? Because I want to find, using the fundamental theorem of calculus, the area under this curve, or in this case, the area of this integral. So I'm going to take the antiderivative of this term, cool, minus 1/2 x squared, that's the antiderivative of that, plus 2x, and I'm going to evaluate that bad boy from negative 2 to 1. Fundamental theorem of calculus says plug in your upper limit first, so 1 goes in here, 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 you get negative 1/3, minus 1/2, plus 2, well that was easy, we should love 1, right? 1's an easy number. 0 is a nice number too, we don't have that though, so we're going to just have to multiply it out. Minus what? Well, plugging in a negative 2 here, I get negative 8, right? But I've got times negative 1/3, so that's 8/3. I've got negative 2 squared, which is positive 4, that's minus 2. And then negative 2 times 2, minus 4. Now some of you are saying, where's my calculator? The rest of us are saying, you know what? I bet if we combine like terms, we should be okay. Negative 1/3, cool. Negative 1/2, yeah, not so much. Plus 2, those are all not very like terms. Negative 8/3, okay. And I can combine those two. Negative 2 plus negative 4 is negative 6, but that's negative, so negative 6 is plus 6. Let's continue our combining like terms idea. 2 plus 6 is 8. Negative 8/3 and negative 1/3. Isn't that negative 9/3? Negative 9/3, that's minus 3. Minus 1/2. 5 minus 1/2. What some of you would call 4.5. What I would call 9/2. 9/2. Okay? So we found the area of the curve bounded by this and that to be 9/2 or 4.5. Okay? So again, I don't think this topic is hard. The setup can be fun, challenging, whatever. Let's do another one. This time we'll use our calculators to kind of help with technology here. Find the area between f of x equals 3x squared, psych, 3x to the third, minus x squared, minus 10x, and g of x equals negative x squared plus 2x. Now, I can do this by hand, but let's just do a little review of calculator skills. So hopefully you can see, I'll set the glare so we can see it there. Looks like we've been doing some calculus on here. So, oh, tangent, yummy, yay. Let's clear that and let's clear that. Away we go, clear. All right, so my first function was 3x to the third, so let's just type it in. 3x to the third minus x squared minus 10x. And again, notice I'm using this x button for each time I need the x. I'm not looking for my variables, okay? So it's just that one right there. That's one graph, and the other graph is negative x squared plus 2x. Negative x squared plus 2x. I could, first, you know, I'm really paranoid about checking the mode, so I'm just going to do it. There's no trig here, but radians, yep, we're still in radians, yay, radians, okay? Next thing, I want to make sure I'm in function mode, because I probably should have checked that even before I did, but I had y equals, so it was good there. Next thing I'm going to do is check my zoom, and I always recommend that you do zoom decimal. And I've got a graph, and I've got another graph coming, and oh no, they don't all fit. Well, that's okay. It looks like I've got some kind of a x to the third curve here, and this second one that plugged in was my parabola. So it looks like I didn't get it all. Okay, but as far as my window width goes, I'm pretty happy. I just need to maybe increase a little bit because I'm finding the area between those two curves. Finding the area between those two curves. So that might be an interesting thing. Let's see, if I change my window, the x-min and x-max are okay. I'm going to change my y-min to, I don't know, negative 10 maybe? And y-max to be positive 10. Let's graph that and just see what happens. So I want to make sure that I see all those intersections. Okay, it looks like I do see this intersection here, right? Because you can see that. Now, would you agree that I'm talking about the area of this section here and this section here? But after that, it's like, what's this area here, right? Because you know x squared is going to be a parabola looking thing, and x to the third is going to be, it starts down and ends up, and then it's not coming back down again, so there's only that many turns in a cubic function, so we're good with that. I think these two do show our intersection. So I could do a couple of things. One thing I could do is actually set these equal to each other and learn how to factor for real, which I do want you to be able to do for real, but let's use this opportunity to review some calculator skills too. Second calc, intersect, curve 1, curve 2, and then guess. So enter for curve 1, curve 2, then walk your spider down to close enough to where it is, and I have an intersection at negative 2, negative 8. Let's write that down. X equals negative 2, okay? And we could say y equals negative 8. I don't think I'm going to need that value. Okay, but it looks like it also intersects here. Well, it kind of looks like 0. Let's just double check that because you don't want to assume. Okay, let's see. Negative 2, second calc, intersect. Excuse me. I have a sip of water there. Negative 2, first curve, second curve. And now I'm going to guess and walk my cursor up closer to this 0.00. And sure enough, x equals 0 is another intersection. And second calc, intersect, enter, because it's just asking you curve 1, curve 2. And get closer to this one, and sure enough, it's at x equals 2. Okay? In setting this up, I'm going to need to find the area from negative 2 to 0. However, what's my top curve? Because I've got some kind of, and I can sketch this on a piece of paper, but I think you can see that the top curve is my cubic function, isn't it? So that's 3x squared minus x squared minus 10x, subtracting that whole quadratic, negative x squared plus 2x. And that's a dx. Loving this pollen. It's back. Okay. The next area I need to add is the area from 0 to 2. Same curves, but wouldn't you agree that I've got a curve now that's my parabola minus my cubic? So it's still the same terms, it's just in reverse order of subtraction. Why is that important? Well, if I were to find that height, if I come up with a negative area, is that going to throw off my, or negative height, isn't that going to add up a different area? Answer is yes. Those are thirds, by the way. All right. Now, one thing I'm going to show you is it's easy to plug this in your calculator. This is y1. This cubic is, or sorry, the cubic is y1. The quadratic is y2. If I quit out of here and get to the main screen, remember, green window gets us to function integral. I can do the integral from -2 to 0. Who wants to type all that in when you've got those values available to you? So I'm going to try to trying to show you side by side. Well, that's going to be glare. I'm just going to put it here and show you what I'm doing. VARs, or you could also do green. I think it's trace. There it is. Y2 and Y1. Remember, I labeled my cubic one was Y1. My second degree curve is Y2. So I'm going to say Y1 minus green trace Y2 dx. And if you wanted to go really crazy, you could type in plus integral from 0 to 2 of y2 minus y1. We're just going to do these separately. So I'm going to press enter and get some number here, 12. So this first one is 12 plus the area from, so green window, function integral from 0 to 2 of y2, green trace, y2 minus, and if you don't like the green trace, there's VARs right here. You can press the VARs button, and it's a y-var, and it's a function value, and you go to y1. Okay, so it's the same. It's all there, dx. Okay, so the area of that second chunk, when the top and the bottom of the rectangles reverse because the top curve took over, is 12 also, interestingly enough. 12 plus 12 equals 24. 12 plus 12 equals 24. Okay? And that is the same answer that I got by hand. Let's look at our graphs again. Would you believe that, yep, indeed, this area here plus this area here, those are both equal areas, would be 12 plus 12 is 24. Okay? Again, reminder, the area from A to B, where those are x values, is going to be your top minus the bottom dx. And this is when you have functions of x, like we had f is a function of x, g is a function of x. What if I had integrals from c to d? I wonder where we're going with this. Well, I'll tell you where we're going with this. What if I have dy? And we'll do an example with that, where we've got values of y, c to d, and if I wanted to subtract those. So we've got, instead of up and down, I've got some function here and some function in here, where I've got a representative rectangle that's setting this up to be a dy kind of problem. Okay? Would it make sense to subtract these from side to side? Well, which is going to be the bigger number? Always the bigger number is going to be on the right, on the number line. So it's right minus left. Right minus left. Okay, so right minus left is going to give you that. All right? So if I've got a dy problem and a representative rectangle that goes this way, we're accumulating now up the y-axis with incremental changes of y, dy, a thickness of dy. I'm going to say right minus left. Right minus left. So let's find one like that. Let's find the area bounded by x equals 3 minus y squared, and x equals y plus 1. I'm going to quickly sketch that. I'm not going to worry about that. It's x equals 3 minus y squared. Well, y is 0. Isn't x going to be 3? So that's our x-intercept, right? And since it's negative y squared, isn't going to be a sidesy parabola that goes opening to the left, the negative side? There's your parabola there. And then I've got the line x equals y plus 1. So when when y is 0, wouldn't x be 1? When x is 0, wouldn't y be negative 1? So you can kind of graph those, and you know it's a line that would go there. So instead, we've got this right here, and I usually will do my representative rectangle in red. It doesn't matter where it goes, as long as it's in the region that because hopefully we all agree that that's the region that we're trying to find the area of. Here, I mean, this is unbounded, right? There's no, how would you know when to stop? Over here, yeah, it's below here, but what's this, right? So the area bounded by that, those are the boundaries. So it has to be inside that boundary. That's what we mean the area bounded by. Well, this time, and our calculator probably is not going to be that much use, right? Because I don't have an x equals button, and I'm not going to worry about trying to flip and let's just go ahead and do this by hand. Our first thing we want to do is figure out where they intersect. 3 minus y squared equals y plus 1. Well, get my y on the other term because I've got a parabola here. Quadratic, I'm going to get a positive term there. Plus y, add that over, subtract, minus 2 plus 1 equals 0. So wouldn't we get 0 equals y squared plus y minus 2? And that again factors to be y plus 2, y minus 1 equals 0, y equals negative 2, y equals 1. That was the same factoring pattern that we had on the first problem. So now I'm going to have an area this time from negative 2 to 1, right? Because again, we're accumulating, these are y values. I'm going to put a dy out here. And I hope that you're seeing that dy, even though I'm saving room before I write it, is really going to help us. Okay? So I'm using this. This is a dy. I'm accumulating along the y-axis. Right is my curve. Now, question, is the right always the curve, the parabola? Even from down here? Yeah. Is the left side of all these rectangles, so I could draw one here, 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 all the way up and down, that region, is it always going to be the right minus the left is going to be the curve minus the line? Yes, I hope you can see that. If you're not seeing that, please practice that. 3 minus y squared minus my other one, and that's why those parentheses are important, right? The whole thing, y minus y plus 1 dy. Okay, dy. So integral from negative 2 to 1. 3 minus 1, well, that's just 2, isn't it? Minus y squared minus y, right? And that's a dy. In fact, if you had your notes from the first problem, this is the same. So let's just practice our calculator again. And I wanted to show you this one using the calculator because a lot of us panic. We don't care about what the graph is. This is x, this is y. How am I going to look at the graph, right? So going to y equals, you don't need y equals. Okay, you were able to sketch that graph good enough. So you know, I watch you when you test. Everybody goes to y equals, then you grab it, and you're hoping well, did you really need to do that? So quit out of here. Let's just set up an integral. Function integral from negative 2 to 1. Let's just type this in. Instead of y, we're going to use our variable x. That's okay. It doesn't know that it's an x value or a y value. We're just saying something squared minus something dx. I mean, just because we're typing it in an x, you know that the problem was really y. Same idea with t. We don't hunt and peck for the t. We just use x because we're setting up an integral. So press enter and we get, 4.5, which is what we had before. But I don't like dirty decimals. I agree. So I'm going to math frac that bad boy, 9/2. And that was the same area that we had of a similar, on the x-axis problem, it turned out to be the same integrand on the y-axis problem. All right, so that's your lesson for today. Get some practice. I might, at the conference this morning, folks said that they liked having My Math Lab. I'll see if there's any My Math Lab problems that are similar to this, but you've got a worksheet that's got some good review problems on it anyway, so that's posted already, and that'll get you going. Probably lesson day today and work day tomorrow. As you heard, we are homeschooling until, well, through the end of April. Who knows when until, but at this point, the earliest we could come back would be May 4th. So I'll give you a work day tomorrow, and I'll hunt up some My Math Lab problems as well. Also, think about end of this week, we'll know more about the AP test, and I'll come up with some ideas for you on how to get ready and start planning for studying for that too. All right. Hope everybody's doing well. Take care. Send me a message or email me if you have a question, and I will talk to you soon. Have a good one.